Thank you everybody for returning to the second part of the tutorials today for the workshop. So I'll begin now with the second part of the tutorial on the foundations of feedforward networks. So as a matter of reminder of the schedule, we began with a tutorial on the foundations of feedforward networks part 1 and then Alejandro. And in the rest of the afternoon, I'll be continuing with the second part of the foundations of feedforward networks, and then Alejandro will give the second part of the foundations of graph neural networks. As for the first tutorial, I think the big key message from the first part was to study the optimization landscape for linear networks. And the main results that I shared were the following: that in the case of linear networks, you can show that if you train the network without any regularization, you can prove that all local minima are global, that other critical points are saddle points, that in the case of a neural network with a single hidden layer, all of those saddle points are strict saddles, which facilitates optimization. But in the case of deeper networks, there may exist non-strict saddles. And the interesting thing was that even though we are talking about training of neural networks, a lot of the results are really obtained using linear algebraic tools. The conditions are all derived based on certain matrices being invertible and whatnot. In the second part of the tutorial, I'll focus on neural networks that are nonlinear, but neural networks that the nonlinearities have a very particular form, that they're functions that are positively homogeneous. And the gist of the results will be that if you have positively homogeneous networks that are sufficiently wide, then the same style of results apply, namely that all local minima are global. Specifically, these will be the key questions of the second part of the tutorial. Are there properties of the architecture that make optimization easier? And as I already mentioned, positive homogeneity will be one. But the other aspect will be ensuring that there is parallel structure in the architecture. And I'll be clear about that in a moment. The second aspect is that all of the results that are presented in the first part of the tutorial have the restriction of the square laws, which is a major simplification, but also didn't have any form of regularization. In this second part of the talk, we will allow for regularization. We will allow for arbitrary losses as long as they're convex. And the regularizers will be positively homogeneous, and they will penalize the complexity or of the network. And with those main assumptions, we'll be able to show results of the following form. Number one, local minimum such that if you have a local minimum and it is such that all of the weights associated with one of the parallel subnetworks are zero, that is a certificate of global optimality. Namely, if a local minimum has all zero weights for one subnetwork, then it is a global minimum. The second result will be that as the size of the network grows, and we will be optimizing over networks with variable size, eventually you get to a situation that gradient descent, or a local descent strategy rather, it's not gradient descent in particular, can find a global minimizer from any initialization. Or in other words, in order to travel from any initialization to a global minimum, the objective function does not need to increase. And that's again because when the network is large enough, there is no local minimum. Okay, so with that introduction, let me get started with the results. So the presentation will have three parts. At the beginning, I'll just state what is meant by networks that are positively homogeneous and with parallel structure. The second part will focus on the same properties, but for the regularizer, positive homogeneity and adapting to the network structure. And the third part, that will really contain the main theoretical results. So the first two parts are meant to be high level. There is not too much technicalities. but the second part will have all the technicalities. And in order to make the presentation simpler, I'll focus first on a particular case, and that is the case of neural networks with a single hidden layer and no nonlinearity. Because in that case, it relates to matrix factorization, and you will see why the results are true at a more intuitive level before presenting the results for the case of general networks with nonlinearities. Okay, so let me begin with the first part. What are the assumptions that we make the architecture in order to have these guarantees of global optimality? So the first property that we assume is that the input-output map of the network is positively homogeneous. What does that mean? It means the following. It means that if we have a network like the one illustrated here, and we scale the weights by a certain factor, in particular, let's say you multiply all the weights by alpha, and that alpha is non-negative. Then you ask the question, what is the effect of that scaling of the weights on the output? The assumption is that the output would also be scaled by the same alpha, but raised to a certain power, and that power is the degree of homogeneity of the network. So immediately you might say, well, is this a strong assumption? Am I restricting the classes of networks dramatically by doing so? So let's see a few examples of existing networks. So let's take the simplest possible example, which is a single neuron with a ReLU nonlinearity. And so in this particular case, if you scale the weights by alpha, and the first layer immediately is just dot product between alpha and the input. So naturally, scaling the weights will just scale the output because this is a simple linear operation. So the only thing we have to worry about regarding this scaling is what happens with the rectified linear unit. So now the input to the ReLU, rather than being z, is going to be alpha times z. And what the ReLU needs to do is to take the maximum between that and 0. Now, because the scaling, and that's why it's called positive homogeneity, because the scaling is non-negative, that's not going to change whether the first argument or the second argument give the maximum. And therefore, we can actually take the alpha outside. So the rectification is not changed by this non-negative scaling. And so as a consequence, a linear transformation followed by a ReLU is a map that is homogeneous of degree 1 by construction. Okay, so one of the most used layers is homogeneous of degree 1. What about slightly more complex layers combining fully connected, ReLUs, max pooling, and some of the other commonly used operations? So let's begin with the same exercise. We will multiply the first set of weights by a factor alpha. And because it is a convolutional layer, which is a linear operation, it will scale that by alpha as well. And then it has a ReLU as a nonlinearity. And we already saw that the ReLU is homogeneous of degree 1. So as a consequence, the alpha will pass the first layer. So here's where the situation is a little different now, because I have the input to the network being scaled by alpha. And now the second layer of weights is also scaled by alpha. So because of that, and because it's also a convolution and a ReLU, this means that we're going to have alpha squared after the second layer. So the first layer multiplies by alpha. The second layer multiplies by alpha again. So we've got alpha squared. Then we get to this nonlinearity that is max pooling, and each input over which we need to take the maximum is scaled by alpha squared. By the way, for those of you who are not familiar, so in max pooling is typically used, for example, in computer vision. You take a region of the image, you have the responses in every pixel in that image, and you take the maximum response in that region to gain invariance with respect to what you're trying to predict for that region. And so again, imagine now that every single pixel response has been scaled by alpha squared, and now you're supposed to take the maximum. Because you've multiplied by a positive or a non-negative quantity, the same pixel will be the one producing the maximum. And so it doesn't matter. You can take the alpha squared and take it outside. So therefore, the alpha square will pass this max pooling operation. The next layer, I think now you got it, is going to be multiplied by alpha. We're going to get alpha cube, and there we are outside. So typically, every layer of a convolutional plus ReLU or max pooling will typically increase the degree of homogeneity by 1. And this property of positive homogeneity is actually true of many architectures: fully connected plus ReLU, convolutional ReLU, max pooling, linear layers, average pooling, max out. There are many possibilities. But an important non-linearity for which this is not true is sigmoids that are not positively homogeneous of degree 1. And this will allow us to get results of global optimality for neural networks with ReLUs, but not for neural networks with sigmoids. Okay, so that was my first point. We assume that the architecture is positively homogeneous. Let me now move into the second assumption about the architecture, which is that we need to have parallel structure. What do we mean by that? What we mean is that we're going to take multiple subnetworks with identical structure and put them in parallel. So to begin with, what is the simplest possible example of that? Let me take the subnetwork to just be one neuron with a single neuron with a ReLU nonlinearity. So I need to construct now multiple such subnetworks, multiple neurons in parallel, and connect them. And so that gives rise to the classical single hidden layer neural network, where every subnetwork is just one neuron. Okay, so this is going to be a particular case of the framework for which the results apply. And as I said, the results are of the flavor: if the network is sufficiently large, then local minima are global. For this particular network, what this is going to say is if the number of neurons in that hidden layer is sufficiently large, local minima are global. Okay. Let me give you now another example. You can actually begin with any network that you want, with as many layers as you like, as many neurons in any layer as you like. The only requirement of the framework is that this subnetwork be positively homogeneous of some degree P. Okay. And so we're going to take that as our prototype subnetwork. And then the construction simply is that you need to put many such subnetworks in parallel with each other. And so this is what's going to happen here. The subnetwork has 3 inputs and 2 outputs. You put them all in parallel and you add them up. Okay. So now this gives rise to a potentially very large network that has the property that it's multiple subnetworks in parallel. All such subnetworks have the same architecture, but the weights could potentially be different. And again, here the theorems are going to be of the form that if the number of parallel subnetworks is sufficiently large, then local minima are global. Third example, getting a little fancier. So take the entire AlexNet to be your subnetwork. This is not exactly positively homogeneous unless you do a little modifications, but by and large it is. I mean, most of the operations are convolutions and ReLUs and max pooling. And therefore, generally speaking, a network with k layers of this form would have a degree of homogeneity k. So now you put many AlexNets in parallel and you add them up, and that gives you a network with parallel structure. Okay, so that was the first part where we talked about properties of the architecture. Let me now move and talk about properties of the regularization function on the weights that's going to be added. So this is the classical regularizer that was used in for training neural networks in the 80s. And this is L2 squared, the sum of the square of the weights. And an important observation is that this regularizer is homogeneous of degree 2. If you scale the weights by alpha, you will get alpha squared because it's just a degree 2 polynomial. So that should be fairly straightforward. In this example, what I have here is a network that has 3 layers. And so what we know is that the regularizer is by construction homogeneous of degree 2. And by assumption, the network has 3 layers. So typically it'll be homogeneous of degree 3. Okay. So one important observation that came out of this work is the fact that these degrees of homogeneity, the fact that they're different is a problem. 2 is different from 3. And the fact that 2 is different from 3, it can be shown that the existence of local minima, it's because you have a network whose degree is different from the degree of the regularizer. So an important assumption moving forward we will make about the regularizer is that it is homogeneous, but is of the same degree as the degree of the network. So if typically you have a network with 100 layers, then you need to construct a regularizer of degree 100. And this might be another potential explanation as to why somewhat the use of regularization was abandoned or was shown not to be great as we move to deep networks, because a regularizer of degree 2 is suitable for networks with a single hidden layer, because in that case, the degree is 2 for the regularizer and 2 for the network. But as soon as you have deeper networks, the degree 2 is not adequate anymore. And so how do we construct regularizers of higher degree? So this is the way we're going to do it. We will start with a network with parallel structure as shown here. And we are going to build the regularizer first at the level of the subnetwork. So let me take, for example, the first subnetwork here. In this particular case, it has 5 weight layers. Denoted by W supra 1 to W supra 5. And the subindex here, W1, denotes the fact that it's the first subnetwork. Okay. So the properties that we require on this regularizer are the following. Number 1, it needs to be positive semi-definite. So the regularizer needs to be bigger than or equal to 0 for all weights. The second property is that it's positively homogeneous. With the same degree as the network. And that is a property that I had already explained before. And so the question is, how do we do that for a network like the one shown here that has 5 weight layers? And so we should build one that is of degree 5. So one possibility is just raise everything to the 5th power and then add them up. But here's another possibility. You can simply take products across layers. And so this is sort of some norm for the weights in the first layer times a norm for the weights in the second layer, and so on and so forth up to the 5th layer. And therefore, by construction, this regularizer on this subnetwork will be homogeneous of degree 5. Okay, and the other important thing is that you have a lot of freedom and flexibility here on what norms you can choose. And so in many applications, maybe you want those weights to be sparse, and maybe you might be interested in selecting something like an L1 norm, or maybe a combination like an elastic net type, L2 plus L1 for each one of the factors. And so this gives you a lot of flexibility on how you impose priors or different regularizers. But this is just one example. The framework is very general. Anything that is homogeneous of degree 5 would be just fine. And then that was the regularizer for a single subnetwork. What we're going to do now is to add them up across all subnetworks. So here, capital or little r is the number of subnetworks, and the total regularizer for the entire architecture is just the sum of the regularizers for each one of the subnetworks. Why do we do that? Well, a key modification relative to the regular training of neural networks is that we are going to allow the number of subnetworks to vary. And the intuition behind that is manifold, but one that I like to mention is that in various ways, this means that the network will be adapted to the data. If the data is not very complex, then maybe with one subnetwork I'll be enough. But as soon as I have more and more complex data, I can add more and more parallel subnetworks. And as I've mentioned multiple times now, the main point is that bigger networks that have more parallel subnetworks, they have a more benign landscape in that local minima will be global. Now, the main point in the design of the regularizer, though, is that you want to penalize the addition of extra subnetworks. And the idea is that the regularizer should become bigger as you add more parallel subnetworks. So that's why it needs to be positive semi-definite. And in that way, therefore, this regularizer will be designed to constrain the number of subnetworks. Okay, so with that in mind, I think I've gone through the main assumptions. This is like setting up a theorem. It says if the architecture is parallel and the network is positively homogeneous, and the regularizer is positively homogeneous, and the regularizer is adapted to the structure, then we can get the local minima are global. And so the remaining part of the talk will be really more technical and really making this more concrete and illustrating why this is true. So as I said at the beginning, I'm going to do that by first going through the simpler example of networks with a single hidden layer, which is, again, reduces to matrix factorization. And then I'll show how those results extend to the case of deep networks. Okay, so let me begin with that. Let me begin here maybe with what's on the far right. So the training of a network with a single hidden layer, U denotes, as you remember from the first part of the tutorial, the output weights, V denotes the input weights, and Y denotes the matrix of labels that I'm trying to predict. And on the right, I have some regularizer on those weights that I'm not telling you how I am constructing yet. But the main point I want to do is to establish a connection between that training objective, which is a training on the weights, and a very much related problem where instead of optimizing over U and V, which is the weight, I optimize over the product of the two, which here I'm denoting by X. And when you do that, either regularizer can, which doesn't need to be the case, but if I could have a regularizer only on X, then the problem on the left could potentially be easier, at least from a landscape perspective. Why? Well, because typically the loss function is chosen to be convex on X. Think about the square loss or cross entropy. They're all convex on the second argument. Then the second aspect is that I am adding regularization over X. What is X now? X is going to be a matrix. So I'm effectively kind of, you give me a matrix Y, I'm trying to find a matrix X that is close to Y and regularize according to X. So a typical regularizer might be that you want to impose X to be low rank, or you might do that with a convex relaxation of the rank, such as the nuclear norm. I'll define that in a moment. But the main point is that this problem on the left is generally convex. In sharp contrast, the one on the right will be generally non-convex because of the product of U and V in here. So the problems on the left show up in low rank matrix approximation, matrix completion. The Netflix challenge is another example, robust PCA problem based on nuclear norm and L1 norms, and so on and so forth. The issue is that the problem on the left could be very, very large if the matrix X is large, while the problem on the weights, it could be smaller, because particularly if X is low rank, then the number of columns of U and the number of columns of V could be significantly smaller. So how do we put these two problems together, and how do we exploit the fact that they may be relatable to each other in order to derive results of global optimality? So pictorially, this is what we are attempting to do. We have a non-convex problem on the weights U and V of the neural network that might have many global minima, may have local minima, whatnot. we are going to construct a new optimization problem on the product space. And the product space here is denoted by X. And the key to the construction is going to be the fact that the optimization problem on the product space, the function, will be a lower bound for the original function. And the global minima will agree. More specifically, f of x is going to be less than or equal to f of u and b for any pair of weights whose product is equal to x. And the minimum with respect to x of the convex function is going to be equal to the minimum with respect to the weights of the non-convex function. That's the gist of the construction. And the rest of the talk is to really try to explain you why this happens. So let me tell you why this happens. And to do that, I'm going to do that with the nuclear norm in particular as a regularizer for what's on the left. So what is the nuclear norm? The nuclear norm is illustrated here. I hope you can see my mouse. So it's simply the sum of the singular values of the matrix. So it's a very simple quantity to compute. You just compute the singular values and sum them up. As it turns out, this very simple and trivial quantity can be computed in a way more complicated manner via the so-called variational form of the nuclear norm. What is that? And let me begin here on the far right. You begin with a matrix X. You factorize it as the product of any two matrices U and V. And then the factorization might not be unique. You may be able to construct many matrices U and many matrices V whose product is equal to X. Among all those possible factorizations, you select the one that minimizes this objective. What is this objective? Is the sum from 1 to R. R here is the size of U, the number of columns of U. And U sub I is the ith column of U. And V sub I is the ith column of V. So it's the sum of products of norms of the columns of the matrices U and V. And the magic of all of this is that if you minimize that with respect to all possible factorizations of all possible sizes, you get the nuclear norm on the left. And the nuclear norm is a convex function of X. What you have on the right is sum of products in the factors is non-convex. But the interesting thing is that the minimum of that is a convex function of the product. So the minimum of a non-convex function on the weights is a convex function of the products. And that's, I think, what's critical. So as a consequence, what we're going to do is to choose the regularizer on the UV space to be exactly this sum of products of norms. And I hope this is starting to resonate a little bit with the introduction now, but a little bit more concretely, right? This regularizer is now homogeneous. It's homogeneous of degree 2. It is actually obtained by taking the norm of one layer times the norm of the other layer. Here, V is the input layer, U is the output layer. V sub I, in the case of a neural network, will denote all of the weights associated with the ith neuron. And R will be the total number of neurons in that hidden layer. So what this regularizer is doing again is for every neuron, you take the input weights and you take the norm, you take the output weights and you take the norm, you multiply them, and that gives you a homogeneous regularizer of degree 2 on those weights. And then you add them up across all the neurons in order to penalize the complexity of that network. And the complexity here is measured in terms of the number of neurons. And as you can see, putting the regularizer in this form will induce a nuclear norm regularization, so, which is sort of the convex relaxation of the rank. And therefore, it's sort of imposing a convex relaxation of counting the number of neurons in that hidden layer. Now, I introduced everything with this nuclear norm here. And the interesting observation is that the nuclear norm is connected to the two norms. So nuclear norm in the product you need the two norms on the columns. But this paper by Francis Back, more than 10 years ago, had already generalized these variational forms to any norm that you might want to put. So this little u here denotes any norm in the u space. This little v is any norm on the v space. And you play identically the same game. And what you get on the left is going to be some UV norm. What is that norm? Well, we don't know. I mean, it depends on the choices that you put. If the U norm is the 2 norm, and if the V norm is the 2 norm, then you get the nuclear norm. But otherwise, it could be the case that whatever you get on the left is intractable or difficult to compute, or you don't even know what norm it is. But the main point is not here to use it as a computational tool, but rather as an analysis tool, namely that we know it induces some norm, and norms are convex. And that's exactly what will allow us to do the construction of building a lower bound to the non-convex problem that is convex. So with that introduction and notation in hand, I can now more precisely state the main theorem. And the main theorem, remember, is if the network is large enough, then local minima are global, or local minima with 0 weights are global. So let me be more specific as to what it means now in the context of matrix factorization, or which is the same as in the context of neural networks with a single hidden layer. So assume that you are given, you have to solve this non-convex training problem. In matrix factorization, you just need to factorize y as the product of uv, and you add this regularizer. Suppose that the loss function is convex. Think again about the square loss or cross entropy. We could have used the L1 norm, but there is a technicality here that we require the loss to be differentiable in X. We believe that is not needed, but for the purpose of this theorem, it's there. So assume that the loss is convex and once differentiable, then a local minimum of this non-convex problem such that for one column I, the column of U and the corresponding column of V are both identically 0. So if you find a local minimum that has one column that is equal to 0, as highlighted here by the black, then that is a global minimum of that non-convex problem. And in addition, the product of U and V is a global minimum of the following convex problem, where again, UV transpose is substituted by X, and the regularizer is substituted by that fancy norm, sort of the generalized nuclear norm that I was talking about before. So I hope this provides now a very precise statement. And I think the intuition behind this simply is the following. You have a loss and you have a regularizer. What does it mean for the column to be 0? What it really means is that you keep adding more and more columns, and eventually there will be 0. Adding extra columns that are zeros doesn't change the loss. Adding extra columns that are 0 doesn't change the regularizer. So that's a characterization of being a local minimum. If those columns were non-zero, for example, another way of stating these results is that the columns of U are linearly dependent. If the columns of U are linearly dependent, right, you can construct change of basis here that won't change your loss. But that would increase the regularizer. So really, what's happened is that this convex problem has a global minimum. This global minimum is, say, of low rank. And as you solve the non-convex problem and you keep increasing the value of R, eventually you hit the rank of that global minimum. And then you stop, because if you keep adding extra columns, then you won't be able to further decrease the objective. In pictures, this is more or less what's happening. The blue curve, again, is the non-convex objective. And let's say that you are at a particular local minimum. You run your gradient descent algorithm of that non-convex problem, and you're there. This idea of adding an extra neuron or adding an extra factor or adding an extra subnetwork is equivalent in an optimization perspective to saying, well, I have another dimension, another variable. I'm changing my optimization problem to add extra variables. When I do that, let's say I have a second variable here, I can ask the question, can I decrease the objective by moving in this new direction? And if I can decrease that objective, then I'm going to move in that direction and keep going down. However, if I was at a global minimum to begin with, if I add an extra dimension, I won't be able to further decrease the objective. And that is exactly what the theorem is saying, that if you try to add it, then you might as well add a zero and you're going to stay in the same place. So this provides the intuition for the second theorem. And the second theorem says that you can actually reach, at least theoretically, the global minimum from any initialization. And the proof of this theorem is really a constructive procedure, which is stated here by this meta algorithm. So how would you, starting from any initialization, reach a global minimum? Well, the way you would do it is as follows. Suppose you begin here. And you are optimizing now, say, with 2 neurons for the sake of argument. And you optimize over the weights of those 2 neurons, and you do your local descent strategy, and you keep going down. And eventually you get to a critical point and you stop. Now you ask the question, well, am I at a global minimum? How do I know? Well, the weights would need to be 0. That was the first theorem. And so clearly here, I'm not at a global minimum. So the answer to the first question will be no, you're not. And so what I'm going to do is that I'm going to augment, add an extra neuron. Once I do that, I'll be able to take a descent direction and continue. So how do I do that exactly? As written here, the number of columns will move from R to R plus 1. The matrix of output weights U will be augmented by an extra column, and the matrix of input weights V will be augmented by another column. That's because I'm adding an extra neuron, so I need 2 new vectors of weights for the input and the output. I am going to choose those extra weights or the values of these new variables that I'm adding in a very careful manner so that I have a descent direction. And once I do that, I'm going to get to this green point, and I'll be able to continue the descent strategy up until I get here. Once I'm there, I repeat, do I have zeros? Yes or no? Well, I don't necessarily at first. So then I try to add an extra column. And then I realize that the only descent direction that I can find is the 0, 0 direction. And that's when I realize that I've arrived at a global minimum, and that's when I stop. Now, I've written this as a meta algorithm because that doesn't mean that doing this is tractable. In particular, determining whether you are at a local minimum can be NP hard for non-convex problems. So to be able to implement this, you still need to develop more efficient methods. Okay, so hopefully that was clear. So far, what is it that I've said? I've said that there are 2 main results. Local minima are global if the size of the network is big enough. And that I've shown how these results are applicable to just factorizing matrices. And the gist of it and the core of it was this sort of nuclear norm type and the variational form to be able to do. So let me now move on how this extends to deep networks and try to generalize each one of the key ingredients of the construction. The first ingredient was this matrix product. So the matrix product, UV transpose, can be decomposed as the sum of rank 1 matrices. And it decomposes over the columns. And each one of the products here is a degree 2. So it's homogeneous of degree 2, which is what we need. So in the case of neural networks, this means I'm summing over the neurons in the hidden layer, and I've got my UI-VI transpose for every hidden layer. So the generalization of that two neural networks is that now I am going to have, and you might remember, I introduced that I have this parallel structure. I am going to have many subnetworks and add them up. Each subnetwork should have the same identical architecture, but they have different weights. And so this little phi map here is the map of the subnetwork, and Wi 1 to k is the weights of the k layers of that network, ith subnetwork. And then I'm going to sum from 1 to r. R is now the number of parallel subnetworks. So as you can see, the outer product, Ui Vi transpose, is the key atomic element of the matrix product. That is now replaced by the input-output map of whatever subnetwork you've constructed. And as I said before, it can have any number of layers that you want. It can have any number of neurons that you want. The only property we are requiring of this little phi map is that it must be positively homogeneous of some degree on the weights. Okay, so that covers the generalization of the architecture part, which I've mentioned earlier. The next one is really what is the generalization of this fancy regularizer that I had presented earlier. So you might recall what we had was this nuclear norm, and the key to everything was that you begin with the output Z in this case, you write that as your product, and then you minimize sums of products of weights essentially. And when you do that, the magic was that you get a convex function of the product. That was the key. So what we're going to do is identically the same. And so now what we're going to do is on the far right here, Z now denotes the output, the matrix of outputs of the network to all inputs in the training set. And that output is a function of the weights. Okay, so give me the output, whatever that might be, then there is or there exists some weights that produce exactly that output. Those weights may not be unique. There might be many weights that give rise to the same identical output. In particular, you might have scalings. I can double one layer and reduce, multiply the next layer by half, right? And there are lots of invariances that exist inside. So the weights are not unique. Among all those possible choices of the weights that give rise to the same output Z, I'm going to choose the weights that minimize the regularizer, whichever regularizer I had decided. Again, here at the top, it was sums of products of weights. The only property that that regularizer must have is that it must be positively homogeneous and that the degrees have to match. So the degree of the regularizer needs to be same as the degree of the subnetworks. And then I'm going to minimize with respect to all possible such weights and also with respect to the number of parallel subnetworks. And I'm going to think of that as now some function of Z. Okay. And that function, of course, depends on my product map and on my regularization map. Okay. So.
Reproduciendo desde Rennes Mapo Pro 2020.
Sorry about that.
Reproduciendo desde Rennes Mapo Pro 2020.
Okay, so with that in mind, here's the key result. That function, omega, is a convex function of Z. Even though phi is non-convex, even though theta is non-convex, this is a convex function of Z. And so the gist is really that the regularizer that we are going to put on the weights of the neural network somewhat comes from a convex function. There is this relationship between building homogeneous regularizers of a fixed degree and putting a convex penalty on the output of the network. So with that, I can now easily, or at least in words, generalize the key and main result, which is the following. Suppose that you give me a loss that compares the labels y to the output z of the network. And suppose that it's convex and differentiable in z. A local minimum of the training objective, which is given here. I'm trying to minimize the loss. Phi, again, is the map, the input-output map of the network that maps the weights to the output. Theta is the regularizer. So a minimum of the regularized training objective, such that for some I, for one of the subnetworks, in all k, that's all layers, has all the weights that are equal to 0. That is a global minimum of that non-convex objective. And in addition, if you take that global minimum and you substitute that you substitute the optimal weights into the input-output map of the network, and you get the output. The output of the network is a global minimum for this convex objective. It is convex because the loss is convex on the second argument z, but this fancy regularizer built as the minimum of the weights is also convex in z by the previous theorem. And again, this big meta theorem requires simply the assumptions of positive homogeneity and everything I've stated so far. And it turns out that many problems in machine learning satisfy these assumptions. Matrix factorization was one that I already highlighted. I didn't talk about it, but tensor factorization is another example where instead of matrix product, you just have tensor products, but those are homogeneous of degree k, where k is the degree of the tensor, and deep learning, which is what I just stated. The second theorem is the same as before, so I'm not going to repeat everything I already said, but the primary difference is that instead of adding one neuron at a time, up until you get the 0 weights, you add one subnetwork at a time. So you will begin with one subnetwork, run your local descent strategy to optimize. Once you find the local minima, you will check if it has 0 weights. If yes, then you're done. If no, you continue. And by continue means you add one extra parallel subnetwork and you repeat the process. And by doing so, eventually you will be guaranteed that after a finite number of additional subnetworks, you will find a global minimum. So to summarize, I think the big messages of this part of the tutorial are the following. Number one, that size has an importance in the optimization landscape. Generally, what we've seen is that wider networks have a landscape that is more benign. And in particular, you can have guarantees of global optimality once the network size is sufficiently large. The results presented here have limitations, though. One limitation in particular is that the notion of size is achieved via this assumption of parallel networks. And so positive homogeneity is not a strong assumption. And as I said already, that many networks are positively homogeneous, linear convolutions, ReLUs, and whatnot. But this assumption of parallel subnetworks is not, these subnetworks are not that commonly used in practice in the literature. And so the question of how do you extend this notion of size, how do you accommodate networks with a variable number of layers, and more broadly, how do you optimize over the network architecture is, I think, a question that is of great importance moving forward. And the framework here would be an optimization framework where you optimize both over the architecture design as well as over the network weights. The second main point is that regularization matters. The second set of results require the use of regularization, and it was done precisely to control the size of the network, precisely because we were optimizing over networks of variable size. This is in contrast with the first set of results for linear networks, where there was no regularization, but the size was assumed to be fixed. So further studying this trade-off of that, in many practical situations, you might not want to vary the size. You are just given a network and you just need to train it, and you want to have guarantees of global optimality. The result presented here will tell you, well, if you keep increasing your size, eventually you'll be fine. And so how do you reconcile both is another avenue for future research. And third, everything I said was primarily an analysis of the landscape. There was not here a consideration yet of algorithms, although I mentioned at the very beginning in the introduction that when the landscape is benign, simple optimization methods such as gradient descent can be, or at least stochastic versions of them, can be proven that they avoid, say, saddle points with high probability. So here, the results are primarily of the landscape. There is no really an algorithm that provably converges to the global minimum here. And the meta algorithm that we have proposed is based on adding one subnetwork at a time. And so that requires finding a descent direction. That can be NP hard. This requires verifying that you are at local minimum, which can also be NP hard. So at the other end, the framework is very, very general. It allows you for any regularizer as long as it's positively homogeneous. So I think moving forward, the question is, can I find quote unquote computationally tractable regularizers, namely regularizers for which the verifying that you're a local minimum or finding a descent direction would be more tractable. So with that in mind, I think we have 8 minutes before the second part of Alejandro's tutorial. So I'd love to entertain some questions.
I have a question of something that I missed, René, which is that some set of results that you have say that the local minima are as good as global minima, but in this second part of the talk, you gave a good discussion on developing new algorithms to find this global minima. So I must be missing something, because if my understanding were to be correct, there would be no need for designing these alternative algorithms.
Sorry, I'm not so sure if I understood the question completely, so let me try, and if I don't get it, just please correct me. What does it mean that local minima are as good as global minima? I'd like to distinguish between the word good can have two aspects, an optimization aspect and a machine learning aspect, and they need not be the same. So from a pure optimization perspective, the theorems essentially say that under certain conditions, local minima are global. For linear networks, it essentially says that all local minima are global. There is no local minimum that is not global. For the second part of the talk, it says that all local minima that have some zero weights are global. So yes, they're all equally good from an optimization perspective, and so any one of them that you find, you'll be fine. But that is not necessarily the same story when you talk about generalization. Some global minimizers might have good generalization properties, some others might not. And so that's why the talk is sort of disconnected from the generalization aspects of the story. So then when it comes to algorithms, everything I was trying to mention was pertaining, well, how would you find a global minimum, regardless of which one? And I was simply trying to argue that depending on the choice of the norm that you use for regularizer, that problem might be easy to solve or might be difficult to solve. And that in most cases, it's actually NP hard to determine whether you are at the local minimum or whether a descent direction exists. but that is still disconnected from the learning aspect. In a sense, what is probably happening is that you just run gradient descent, and it happens to go in particular directions, and you get to one of the global minimizers that has good generalization properties. And that's the part of the aspect that requires the interplay between optimization and generalization to study why. Let me stop there because I'm not so sure if I answer your question exactly.
Yes, almost. The related question is this. I mean, then like the saddles are degenerate, but is this really a problem in practice? Meaning, do you really get stuck in saddle points?
So there is a series of papers, and I had them in the references in the introduction, showing that you can escape saddle points with high probability. Beyond that, in fact, there is a series of papers talking about optimization problems with strict saddles. So is it a question of whether, in practice, you will just run your algorithm and what is the probability you will get stuck? Maybe it's not a question of the fact that you will actually hit or converge to a saddle point always, but the fact that the algorithm might significantly slow down around saddle points. So I think this is a very active area of research right now, trying to establish conditions under which local descent methods such as gradient descent or stochastic variance avoid those saddle points. And there's various papers. In the case of matrix factorization is generally well studied and acknowledge the fact that you can avoid them. But in general, it's not, I don't think the more general case is fully studied yet.
Great, thank you.
Oh, yes. The last question is there will be results pertaining to dropout. I unfortunately ran out of time, so I didn't get the time to present them. So I apologize for that. But if I may, I can just briefly state the results pertaining to dropout. Let's see if I can just find one slide. I think this is a good summary of what I was going to say, but I decided to give the time for questions. We've done an analysis of dropouts and shown the following major conclusions. One is that it is a stochastic gradient descent method. The second one is that it induces low rank solutions. The third one is that the weights are balanced. And if I could just maybe show this slide, the gist of it at the end of the day is that if you think about the same matrix factorization like loss that I was talking about, you introduce this dropout variable z in the middle of it. And you now take the expected value with respect to the dropout variables. Then that expected value can be computed in closed form, and it's exactly equal to the square loss, the one that you thought you were optimizing with dropout, plus an explicit regularizer. And this explicit regularizer has exactly the form of sums of products of weights that I was talking about. And the primary difference is that there is the squared is the product of the square of the weights as opposed to just the product of the weights. And so there is a little bit of imbalance of homogeneity. This is now degree 4, while your product is degree 2. But despite that, despite that, you can still show that this is related to the nuclear normal square. Let me stop there, not to take more time from Alejandro. The last question that is in there is how the results.
Yeah.
Mm-hmm.
Yeah, you can take the
there
question.
There is a question about how it generalizes to other laws. The main assumption that we've made is that the loss needs to be convex on the output of the network. I don't think we've thought about it in the context of training generative models with a KL divergence, but certainly it applies to cross entropy or L2 squared or any loss that is convex or and once differentiable.